Welcome, ladies and gentlemen, to our second lecture on kinematics in multiple dimensions. Today what I want to do is solve some example problems where we have systems with constant acceleration and motion in multiple dimensions, just so that we can get a better feel for this and so that we can look at some properties of this motion. So the first example here considers the simplest kind of constant acceleration, zero acceleration. So remember that acceleration is the rate of change of velocity, and a constant velocity has no rate of change, so the acceleration is zero. The existence of zero acceleration defines constant velocity, so we'll always have a constant velocity if our acceleration is equal to zero. So let's look at our example. Consider two cars racing. They both come around the last corner and onto the final straight. Both cars are 5 meters apart and perfectly even coming out of the last corner. Both cars maintain a speed of exactly 90 meters per second all the way to the finish line. However, one car drives perfectly straight to the finish line 500 meters away, while the other is off from the straight path to the finish line by 2 degrees. We know that the car that drives straight will win the race because it has a shorter path to the finish. But how far behind will the second car be when the winning car reaches the finish line? If the second car's path is tilted by 2 degrees toward the first car, will the cars collide before the finish line? So let's look at what we have here. We have car 1 and car 2, and as they come around the last corner, they're dead even. We have the finish line some distance away. That distance is 500 meters. And car 1 is going to drive straight there. Car 2 is going to not drive straight there, but actually be off by an angle phi, where phi equals 2 degrees. V01 equals V02 equals 90 meters per second. And let's pick our coordinate system like this. So we have x in this direction and y in the direction going forward. And we'll pick the origin such that y01 equals y02 equals 0. And then we'll also choose our origin so that x0 of car 1 equals 0 and x0 of car 2 equals minus 5 meters, because we have it drawn here 5 meters to the left. Then what it wants to know is, what is y final 2? Which is the same as asking, what is y2 when y1 equals 500 meters? So y final 1 equals 500 meters. So now that we have our problem drawn out, we should remember one final thing. The cars are going to drive with a constant velocity, so a1 equals a2 equals 0. Okay? And now let's solve this with 2D kinematics. So we're going to use the equation x equals x0 plus v0 t plus 1/2 at squared. So first let's consider car 1. Car 1 has no motion in the x direction, so we're not worried about that. In the y direction, y final 1 equals v0 1 times t. So that's for car 1. That one was nice and easy. He's just going to drive perfectly in the Y direction and cross the finish line. So now let's look at car 2. In the X direction, X final of car 2 equals X naught of car 2. And remember, that was minus 5 meters. I forgot to write it when we changed pages here. X naught of 2 equals minus 5 meters. So let's put our minus sign in now. I usually like to put in my minus signs when I put in the variables. Plus V naught of car 2 times T. And remember, this is just the X component. And if we look up at the top here, this X component is opposite the angle. So this is a sine phi, okay? V naught of car 2 sine phi is the X component of V naught. And then Y final of car 2, remember Y naught is 0, and the acceleration is 0. So we're just going to have V naught of car 2 times T. And in this case, we want the Y component, and that's next to the angle. So the Y component is V naught of car 2 cosine phi. So we know car 1 finishes at time T equals YF1 over V naught 1. Okay? And then the question is, what is the Y coordinate of car 2 at that time? So YF2 equals V naught 2, and then we'll replace T with this expression that's equivalent. And remember that V naught of 2 and V naught of 1 are actually the same. So YF2 equals YF1 cos phi. And then technically, the question asks us how far behind is it. So the distance behind we'll call D sub B, the distance behind, is Y of car 1 minus Y of car 2. And you can see Y of car 2 is just Y of car 1 times cosine phi, which means that this is equal to Y of car 1 times 1 minus cosine of phi. That will be our distance behind. The unit check is really easy. We have meters and meters, so the units work. That's nice. And sanity check, we can see that as this angle gets larger, right, cosine, as we go from 0 to 90 degrees, will just get smaller and smaller. So the further off he is from straight, the further down, the further behind he is when he finishes. And that makes sense too, because he's making himself drive more and more to the side instead of driving straight to the finish. So sanity works. So units, meters equals meters, sanity, distance behind goes down as phi goes up. That makes sense. We just talked about that one. And then the other one, the distance behind, goes down as Y final of car 1 goes down. So if they aren't as far from the finish line, he won't finish as far behind, right? That makes sense too. His problem is that he's driving to the side a little bit. So if they don't have to go as far, he won't fall as far behind. He's just falling behind a little bit more and a little bit more the further they drive. Okay. So then we plug in numbers. And at the finish, let me come up here, dB equals 0.3 meters. About a foot. He finishes about a foot behind. Okay? But then it had a second question. If the second car's path is tilted by 2 degrees toward the first car, will the cars collide before they finish? So the question then is, how far, if this thing up in here, instead of being tilted to the left away from car 1 like I drew it, what if he was driving like this toward car 1? And so all we have to do is go back to here and plug in what we know. So again, let's plug in for t. This expression that we've derived that's equivalent to t. Okay. And that gives us the final x position in terms of things that we already know. And again, remember the V0 of car 2 and V0 of car 1 are the same. And this is our answer for 2. We can see for units that this is meters equals meters plus meters. So that works. And for sanity, x final goes down as the magnitude of x2 goes up, okay? So if we move him further to the left, then his position will be further to the left. That makes sense, okay? And then x final goes up as y final of car 1 goes up. So as the finish line gets further away, he's even further and further to the right because he's off by this angle the whole way. That makes sense too. Okay, and this gives us a final x position of 12.45 meters. This is much further than the 5 meters between them. And remember that he was only 0.3 meters behind, right? That's much less than a car. So if he went this far over and he was never more than a foot behind, yes, they would collide. So the second problem that I want to look at is a projectile motion problem. And this one has a really short little setup here. So consider throwing a ball. If you release the ball at a point 2 meters above the ground with a velocity of 20 meters per second, how far can you throw the ball on flat ground? So it looks like this. We have a ball. It's 2 meters above the ground when you let it go. You give it some velocity, V0, at some angle theta above the horizontal, and it flies out on flat ground and lands somewhere out here at a point we'll call x final. Okay, so let's set up a coordinate system with x in the horizontal and y in the vertical. Let's set our origin such that x naught equals y final equals 0. So we've picked it so that the x coordinate initially is 0, But the y final, when it hits the ground, that's 0. So our origin is right here. 0, 0. Okay? We can always pick an origin to make certain quantities 0. And in this case, with this setup, this is how I'm going to set it up. So then y naught equals 2 meters. V naught equals 20 meters per second. A equals minus G equals minus 9.8 meters per second squared. And the question is, what is XF? So remember that we solved a similar problem for Cool James when he was going to throw the ball, but he released it at the same height that we cared about at the end, right? So the initial height and the final height were the same. In this case, you can see that's not true, right? These are not equal. So the question first is, when I go to throw my maximum distance, is the best launch angle still 45 degrees? Will I still throw it the maximum distance with a launch angle of 45 degrees? Does it change when we're launching at a height that's above the landing point? And the answer is yes, it does. So the first thing I want to do is just consider this problem generally, and let's just look at what the optimal angle is depending on the height that we are above the ground. Okay? So we're still going to look at this with 2D kinematics. And we're still just going to use the equation x equals x naught plus v naught t plus 1/2 at squared. Okay, so let's look at this problem. In the x direction, we have x final equals v naught x times t. X naught is 0, and acceleration in the x direction is 0. So this is good. This is just like when we did it for Cool James throwing, where the launch height, the initial height, and the final height were the same. But then when we look at the y direction, remember we chose our coordinates so that y final was 0. But y naught is not 0 this time. It's some height above the ground. Alright? Plus v naught y t. And then remember our acceleration is down. And we chose a coordinate system like this. X horizontal, y up. So we have minus 1/2 g t squared. So this one we can see it's a little bit different than Cool James. Now we have this little guy in here, okay? And that messes us up a little bit. So now we want to look at this and see how does that affect the optimal angle. So we're starting from just those equations there. So the first thing is, if we do a little cutout here, I'll show you guys again. If we have some angle theta, we can see that v naught x is next to the angle, and v naught y is opposite the angle. So v naught y, actually let's write it up here. V naught y equals v naught sine theta, and v naught x equals v naught cosine theta, right? Cosine for the one that's next to the angle, sine for the one that's across from the angle. So that tells us that we can rewrite t as equal to xf over v naught cosine theta. And then we can put that into our equation for y. So we have y final equals 0. That's y naught plus, remember v naught y is v naught sine theta, times t, which we said is x final, over v naught cosine theta, minus 1/2 g, and then t again, squared. So now let's rearrange and simplify a little bit. We have 0 equals y naught plus. Notice that our v naughts cancel up here. This one and this one cancel. Okay. And we've xf. And then sine theta divided by cosine theta, that's tangent theta. I would strongly recommend for this class that you guys have a table of trigonomic identities that you go to so that you can use some of these manipulations that you're about to see me use. Okay? One identity is that sine theta divided by cosine theta, that's tangent theta. Okay? Minus 1/2 gx final over v naught squared, and then 1 over cosine is secant. Secant theta equals 1 over cosine theta. Okay, so we're going to say secant, secant squared. Okay, so then we're going to use, we want to know the max distance here. So if we want to know the max distance, we're going to use our same calculus trick that we've used before, and we're going to take the derivative with respect to theta. So on the left side, we still have 0. And on the right side, we're going to take the derivative with respect to theta of everything on the right side. And remember, this x final is a function of theta, okay? So let's just make this real clear. D theta, and then this. Okay? And then, just as an aside real quick, I'll tell you that d theta of secant of theta equals secant theta tan theta, okay? And d theta of the tangent of theta is equal to secant squared theta, okay? So there's that information. Let's work from that. All right, so we're going to work from there. The y naught is really simple. It's not a function of theta, so the derivative with respect to theta is 0. So that one's just gone. The next one, you'll notice we have to use the product rule. Remember, I said xf is a function of theta, okay? So let's just write it dxf d theta, because we don't know what function of theta is, okay? But we know it is a function of theta. We know it does vary with the angle. And then times the second, tan theta, plus the first, xf, times the derivative of the second, the derivative of the tan theta, which is our secant squared theta. Okay? And then over here we have the same thing. So we have this when we take the derivative of the xf part with respect to theta, and then when we do the secant squared theta part over here, we get this piece. Okay, so that was us taking the derivative with respect to theta. And then remember, to find xf max, we set dxf d theta equal to 0. Okay? We impose that condition. So when we do that, we have a new equation. We have 0 equals xf secant squared theta, because this is 0 and this is 0, so those two terms go away. So we have this first term minus this second term. So now we have this new equation, and we can solve it for xf. Okay, so then we've solved for xf. And this cot, this is cotangent. It means 1 over tangent theta. Okay, that's cotangent. So instead of sine over cosine, this is cosine over sine. So remember from before, we solved for t in the x direction, and then we plug that into our y equation. And we got an equation like this. But now we've solved for xf when we want to make xf maximum, right? So this is xf max. So now if we take that and plug that into our equation from before, we get a new equation. And then we can take this and we can simplify a little bit. We know that this is 1, right? And we know that we can do some canceling here with the g's and the v naughts. So let's rewrite our equation. So we can rewrite it like this. And now with this new one, a cosecant, the CSC, equals 1 over sine theta. Okay? So let's get the 2 g's. Let's multiply the whole equation by 2g to get these g's off the bottom. And to get this 1/2 to get rid of that. So we have this. And then let's pull this 2 v naught squared apart so that it's just 2 sets of 1 v naught squared. You'll see why I did that in a second. And then that is equal to, but this piece here also has a trigonometric identity, okay? And the trig identity for this one is that this piece is equal to minus cotangent squared of theta, okay? So let's rewrite our equation, putting that in for this 1 minus cosecant squared. So we have this new equation right up here. And let's rearrange this one now. We've got the 0 on one side, so let's bring this term over to the left and write it like this. And then when we do that, we can just solve it. We can take the square root of both sides and have this. And And then we can divide by v naught. So that'll bring it over here. So we divide by v naught and it comes over here. And then just because cotangent is kind of goofy, I'm just going to change it to tangent. And remember, cotangent is 1 over tangent, so all I have to do to the right side is flip it to make it tangent. So tangent theta is equal to v naught over this piece. And that means that theta is equal to the arctangent. This, when we have a trig function like this to the -1, that's kind of a funky notation, but it means arctangent. It means I take the stuff inside, and the arctangent will return the angle that if I plugged that angle into tangent, it would give me that quantity. Okay? So, in this case, it's v naught over 2 y naught g plus v naught squared in a root. So what this is telling me is this is going to give me an angle that if I put this angle into the function tangent, it would give me this quantity right here. Okay? So that's arctangent. And this gives us a really nice expression for theta in terms of the things we know. So notice now that I have my angle for maximum distance, and it just depends on v naught, y naught, and g. Okay? All things that I know. I'm going to know where I launch it from, and I'm going to know how fast I launch it, and then g, of course, is always the same. So this, the reason we spent all that time to derive this is a really generalizable result. Okay? So it's an expression for theta that only depends on those quantities, and it works anytime I choose coordinates that make y final equal to 0. Now remember, in our other case, we just had that y naught was also equal to 0. Okay, so we had this same equation should hold true. Remember when we had the Cool-James example where the initial position and the final position were the same height, that would make y final 0 and y naught 0. So it would make this term 0. And I'd end up with, you can see I'd end up with v naught over v naught, or 1, and tangent equals 1 when the angle is 45 degrees. So it returns the same answer that we got before when we plug in the same y naught that we had before. But now this one is general. This works for any y naught. So we can be any height above the landing point, above the point where it's going to hit the ground, and this will still be true. So now this theta is a much more general answer, and I derived this so that you guys will have it in the future. So make sure you write it down. Make sure that you have it so that you can use it on your homework or your tests or whatever in the future. This is a general example for this, okay, or a general solution to this. So theta max equals, or theta for the max distance, the arctan of v naught over 2 y naught g plus v naught squared, all in a root. So now remember that we had this expression right here for xf but now we have an expression for tangent of theta, right? It's the stuff in here. So 1 over that, or that thing flipped, is cotangent theta. So this is equal to v naught squared over g, and then times this piece, right? The tangent of, or the cotangent of theta. So now this cancels and this cancels, and what I get is xf equals v naught over g 2 y naught g plus v naught squared. Okay, and this now gives us an expression for the f for x, let's say x max, the maximum range when we have some height here. Okay, so now we have a maximum range that doesn't depend on the launch height and the landing height being the same. This height is general. So this range is general for any starting height. And this one is true, again, when we know y naught and v naught, and we choose coordinates so that x naught equals y final equals 0. Okay? So that's true of this one and of this one. So this gives us our angle for maximum distance and the maximum distance that we can have an object fly in projectile motion any time that we know just y naught and v naught, and so long as we choose coordinates so that x naught and y final are 0, because that's what my derivation relied upon, right? That's the way I set it up to get these answers. But these are really useful, really general answers that we got out of just considering this problem, right? This doesn't even have anything to do with our specific problem per se. This is just a completely general example that is going to be useful to us in all kinds of situations later. So these two are things you should write down: x max and theta max, okay? The maximum range for projectile motion and the angle that produces that maximum range, okay? And the whole reason I spent all this time deriving this is because these are really general, really useful expressions for this that only rely on knowing the initial height and the initial velocity, okay? And then we just set up our coordinates so that everything works out. So now let's return to our particular problem. Our problem asked us, how far can we throw it if we release the ball 2 meters above the ground with a speed of 20 meters per second? What's the maximum distance we can throw it? Well, now we have our general answer, and it's just a matter of plugging in numbers. So we have x final equals v naught g root 2 y naught g plus v naught squared. Okay? This is the answer. Now, we derived this thing and I didn't really check it, so let's go ahead and check it real quick right now before we plug in the numbers. The units. We have meters per second squared, and then inside the root we have meters times meters per second squared plus meters squared per second squared, all in the root. And that's equal to, you can see these meters cancel, this second cancels one of these, that's seconds, times meters per second, which is equal to meters, as it should be. So that's great. Units work correctly. Sanity. Let's think about it for a second. If y naught goes up, x is further. So x final goes up as y naught goes up. So if I throw it off of a higher height, I can throw it further. And this makes intuitive sense to us, right? This makes sense. As we go up, we give the ball longer to fly, and we can throw it further. We also have xf goes up as v naught goes up. Notice it's in the numerator over here, right? And then the numerator again here. So as v naught goes up, xf goes up. And that makes sense. If we can throw the ball harder, if we can just give it a faster velocity to start with, we can throw it further. Again, that makes sense. Okay, so then we just plug in numbers. And what is x final? So x final is 43 meters. So we can't throw the ball as far as James was throwing the ball, but that's because, again, up here, we're not throwing it as hard, right? But we got the answer nice and easy once we did all the work to derive these two equations over here, okay? And then another question is, so what is this theta for theta max? We know that if the launch height and the landing height are the same, it's 45 degrees. But in this case, what was theta max? What did we have to throw it at to get maximum distance once we consider that we're letting it go 2 meters above the ground and then throwing it on flat ground? So in this case, the optimal angle was 43.7 degrees, okay? So it's just a little bit flatter than it would have been if we were throwing to the same height that we were letting it go, okay? So that's interesting. We can see that the angle got a little flatter as we moved our release point above the landing point, and we can see that we threw it this distance. But now, let's consider, what if we went a little higher? What if we threw the ball from the top of a house that was another 3 meters above the ground? Okay? So now we're a total of 5 meters above the ground. How far can we throw it then? So when y naught equals 5 meters, then our maximum throwing distance, let's call these xm instead of xf. So then our maximum throwing distance is 45.5 meters. And theta m is 41.9 degrees. So you can see, as I go up, I can throw it a little further, but my optimal angle gets a little bit flatter, right? And as I go up again, I can throw it again further, and the angle again gets a little flatter. So what if we take it again? What if I was on top of a high-rise? Say I was up on the 37th floor, so 36 floors below me. Each floor is 3.1 meters. So I'm 111.6 meters above the ground, meaning that with my 2 meter high release point, the launch point is now 113.6 meters above the landing point, the ground. So now how far can I throw it? So y naught equals 113.6 meters, okay? Then what is x max now? Now it's 105 meters. And in this case, theta m up here is equal to 21.3 degrees. So now we're getting a pretty flat angle to get max distance, okay? And now I'm throwing it much, much further. I'm throwing it 105 meters. But I'm releasing the ball at a point that's like 23 times taller than when I was on top of the roof, but I'm only throwing it a little more than twice as far, right? Twice this would be 91. I'm throwing it 105, so I'm throwing it a little bit more than twice as far, but I'm 23 times as high up as I was. So my maximum range is increasing as I take my launch point higher, but there seems to be diminishing returns as I go up. It's not a linear relationship where I can throw it twice as far if I go up twice as high. I get kind of diminishing returns. The higher I go, the less difference it's making in my distance that I can throw. So what if I went twice as high as that? So what if now y naught was 225 meters? Well, now what am I going to get? Well, now my distance, x max, is 142 meters. Okay? So now I went up twice as far, but I only got a 50% increase. It only increased by half. Okay? For double the height. So I'm really getting these diminishing returns here, and my angle again, flattens out even more. Now it's 16.1 degrees for the maximum. Okay? So the higher up I go, the more I get diminishing returns on this. The reason that it works out this way is because the longer the ball falls for, and as I'm higher up, I'm letting it fall for longer and longer, the more speed it gets in the y direction, right? It's falling faster and faster in the y direction. But if you remember our equation for x, for the velocity in the x direction, there is no acceleration, right? So v sub x equals v naught sub x, right? If we're using the equation, remember that v equals v naught plus at. So when there's no acceleration in the x direction, v always equals v naught. So as I get more and more speed in the y direction, and the speed in the x direction stays the same, then I'm pointing my speed or my velocity vector more at the ground, right? So when I'm 10 meters up and I throw the ball, it goes like this, okay? But then if I'm another 10 meters up, see how much I'm already pointed down? And it just points even increasingly down as we go, all right? So as I go out as I keep going up, I keep giving it more and more time to add speed in the y direction, but the speed in the x direction never changes. And so as I go up, this has a velocity vector that's pointed more toward the ground than it did when I threw it from right here, right? And I got something that was terrible. And I got something more like this, right? So that might be this much of it. So the takeaway from this is that I can throw things further by going up higher, but especially when I'm throwing them at kind of a low speed like this, okay, I get really big diminishing returns in how much extra distance I get compared to how much extra height I go up. So now let's look at one last simple example here. Sandy is competing in the long jump. The long jump involves a runner sprinting toward a mark and jumping from that mark as far as they can on flat ground. If she manages to jump 6.71 meters when launching from a 40-degree angle, what is her velocity at the time of launch? If that velocity is the maximum that she can produce, could she ever jump any further than her 6.71 meters? So let's start by drawing a picture. So we have Sandy. She's jumping. So she has some initial velocity as she leaves the ground, v naught. It's some angle theta above the ground. And then she's going to follow projectile motion and land somewhere along the ground, xf. I'm going to choose x in the direction of the ground, y in the vertical direction. And then I'm going to choose my origin so that x naught equals y naught equals y final equals 0. We know that x final equals 6.71 meters. We know that a equals minus g equals minus 9.8 meters per second squared. And we know that theta equals 40 degrees. And the question is, what is v naught? Oh, not squared. What is v naught? And then the tag question is, could she ever jump any further than 6.71 meters? So is xf equal to x max? This is 2D kinematics. So we're going to solve it with the kinematic equation. So now let's look at our motion in each direction. So in the x direction, we have x final equals, remember x naught is 0, so v naught x times time. And that tells us that we can rearrange and say that time is equal to xf over v naught x. And then in the y direction, y final equals, remember y naught was also 0, y final was 0, so we have 0 equals v naught y times t, and remember that g is down and our y hat direction was up, so we have minus 1/2 g t squared. We can take our expression from t above and plug it into this equation so that we have v naught y times x final over v naught x minus 1/2 g x final over v naught x quantity squared. And then we can rearrange this equation to bring this term over to the left side and replace our 0. So we have g xf squared over 2 v naught x squared equals v naught y over v naught x times xf. We can divide both sides by xf, and that gives us this. And then remember that v naught x is this up here adjacent to theta, so it's v naught cosine theta, and v naught y is going in this direction, so it's v naught sine theta. So this is going to be v naught sine theta over v naught cosine theta. The v naughts cancel, and we just have tan theta. This is also the v naught x. So let's replace that as well. We get gxf over 2 v naught squared cosine squared theta equals tan theta. Let's bring our v naught squared up here and the tan theta down here, right? So we're going to multiply both sides by v naught squared. We're going to end up with v naught squared here. And then we're also dividing both sides by tangent theta. So what's left on this other side, 2 cosine squared theta tan theta. And then remember that tangent of theta is sine theta over cosine theta. We have a cosine here, so then we have g xf over 2 sine theta cos theta. And then this piece is a trig identity. This is equal to sine 2 theta. So we have v naught squared equals g xf over sine of 2 theta. And we wanted to know v naught, so we just take the square root of both sides. And there's our answer to the first question on this. And I want to make an example of myself here. So I'm gonna let you guys behind the curtain for a second. The first time that I recorded this, when I was doing the math, at some point I just forgot to write this squared up here. Okay? And so when I finished, I didn't have the square root here. And what happened was I got to this answer, and then I said, okay, let's check the units. And you can see that we should have meters per second because we have a velocity. And then on the other side, I have meters per second squared times meters. Okay? And when I looked at the units, I thought, oh, man, they're squared. It's wrong. The answer is wrong. And I knew immediately what mistake I made. I was like, oh, man, I dropped that square on accident without actually taking the square root. So I want to let you guys in behind the curtain here and see the mistake that I made the first time I recorded it, because I caught it with units. This little check that I'm telling you guys to do, that's how I caught my mistake and knew that I needed to re-record it so that I would actually get the right answer here, so I wouldn't make my little goof when I did the math. Okay, so this thing is really important. This can be a really good tool for helping you make sure that you didn't make a stupid little goof like I did when you're doing a problem on the test. Okay, checking your answer is really important. So then sanity. When we look at the sanity here, we see in our equation that V naught will go up as XF goes up. So what is that telling me? So that's telling me if she had jumped a further distance, she must have had a higher velocity at the beginning. Well, that makes sense. If you want to jump further, you have to leave the ground going faster. So that makes sense. Okay? I also see that V naught goes up as G goes up. So if she had jumped the same distance XF, but the acceleration from gravity was bigger, she would have had to jump harder, right? She would have had to jump with a greater velocity. She would have had to leave the ground with a greater velocity. And that makes sense too. If gravity pulled her down even faster, but she managed to go the same distance, she would also have to jump harder. So that sanity check also makes sense. So then all that's left is to plug in the numbers. And if we plug in the numbers, we see that V naught equals 8.17 meters per second. Or 8.2 meters per second if we use significant figures from our angle here. Okay? So then the second part of the question, it just asked, is XF equal to X max? Okay? This one we don't even really need to calculate to solve. We know that for Y naught equals Y final, theta max is equal to 45 degrees. That's what we did the first day that we did kinematics in multiple dimensions, right? So if that's true, and we see that theta is not equal to 45 degrees, then the answer is yes, she could jump further with the same V naught. And that's it. We've answered that question entirely, both parts. The one part we did the calculation for, all this stuff, and then this part we just had a little logical progression and answered it that way. So next lecture, I'm going to do a few more examples for you guys of kinematics in multiple dimensions, and hopefully between the lectures with the examples and your homeworks, you're getting pretty comfortable with solving problems for kinematics in multiple dimensions.